myself psyched up.
Go ahead.
Okay. Is it going?
Yeah, you're on.
Okay. So, the first thing we want to talk about is Z effective or effective nuclear charge. Okay? Same thing, ZF is effective nuclear charge. So, what the heck is effective nuclear charge? Let's say this is an atom right here. Does this show up? Is it too high?
You're just about at the brink. You can't go any higher.
Okay. So let's go right here. So let's say that this is the nucleus of your atom. And it's got lots of positive charge in the middle, in there. And then we have one shell above that, and then another shell above that. In this shell, you have an electron, and there's an electron. And I'm going to draw with a different color now. We've got an electron over here, and an electron over there. What looks disgusting? It's coffee. It's fine. Frown. Now, what Z effective means is the charge felt or experienced by these outside electrons. So let's just pick this one right here and say, what do you experience? Well, in this atom right here, if everything's all neutral, and this is a neutral atom, we've got 1, 2, 3, 4, 5 electrons. So we must have how many protons?
5?
5, yeah. So there's going to be 5 times 5 protons in the middle, right? So that makes sense. So now we've got 5 protons in the middle. We've got 5 electrons along the outside, right? So the formula tells us for Z effective that we have the number of protons minus the core electrons. Z is the number of protons. S is the number of core electrons. So this is protons. This is core electrons.
Protons are the ones in the middle.
Yeah, exactly. These things in the middle, the things that are positively charged. We got 5 of those. So now we can tell what the Z effective or the effective charge felt by these outside electrons is by just knowing which atom it is.
And it's always neutral?
Well, in this case, it's neutral.
Well,
I can give you an example of one that's charged, if you like.
So
There's
that
quizzes about this as well.
5 minus 3.
This is 5 minus how many? Now this is core electrons. These are valence electrons.
Oh.
So how many core electrons we have? We've got 2. 5 minus 2 is 3. So our effective nuclear charge here is 3. Okay. And now, if you take this atom and you look at the periodic table. So here's a periodic table. Okay? There's a periodic table. Now, this atom right here, boron, is right here on the periodic table. I think. Yes, it is. So if you're counting the columns, or the groups, which is another word for the columns, you gotta know that vocabulary. The columns are the groups. You got 1, 2, 3, 4, 5, 6. So, these are the different groups here.
We have to know the column
Hold on.
things because I'm colorblind.
These are the different groups here. Right? This is how many valence electrons are above the groups. Right? So, this group right here has 3 valence electrons. This group right here has 4 valence electrons. That group right there has 5 valence electrons. That group right there has 6 valence electrons. Right? All of those elements in this group right here, they have the same number of valence electrons. You can try it out yourself if you want to do an electron configuration for any one of those elements. Okay, you can pick one. For our case, we just did boron, which was right here. So it has 3 valence electrons. And look at this. Our answer to the Z effective is 3. It always works out for Z effective, or the effective nuclear charge, that the valence electrons equals the effective nuclear charge if this atom is just neutral. So if it's neutral, it's just the number of valence electrons.
So it's always going to be like that?
So it's always going to be like that.
Okay.
But, now let me throw a little curveball at you. Alright, Ben?
Fine.
I love curveballs.
I know you do. Here we go. Let's erase part of this. And I'm going to say instead of this atom right here, which is just boron, regular boron atom, let's do sodium +1. A positively charged sodium sodium. How many electrons does sodium normally have? Or let me just back up. How many protons does sodium have? Sodium. It's on the very left-hand side. 12. Is that right?
No, it's
11.
11.
That's
You're
pretty
close. Alright, so sodium has 11 protons.
No, I don't know.
Okay? It normally has how many electrons? 11.
Oh, 11.
Normally 11, but now since this is positively charged 1, that means there's one less electron. Okay?
No, but the protons are still a lot.
Yeah, that's right.
There was
One less electron. Why is it one less electron? Because electrons are negatively charged, so if you take one of them away, the whole atom's going to be positively charged. Okay? So this has one less electron. So when you're filling in your diagrams look like this. Okay? These little boxes that we fill in, right? So we have 1, 2, 3, 4, 6, 7, 8. Okay? When you fill in your little diagrams like this, and then you normally have something like that. Here's the first level, here's the second level. Since we now have only 10 electrons, you can fill in these boxes 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10. I think that's 10. 1, 2, 3,
Yeah,
4,
because it's 2 and 8.
How are we doing this?
yeah. 8. So we got 10 right there. We would have normally had 11 right there, but now we don't because we've taken away an electron, right? So now if we do this formula like we just did for the ZF, it's a little bit different now for sodium. Because normally sodium would only have 1 for its Z effective. But now we've got 11 protons, right? 11 protons, and we're going to subtract the core electrons. But now, since these are now the valence electrons, we only have 2 core electrons. Okay, so this is the weird case where if it's charged, you have to use this formula. And I'll give you this formula, if you would. I'll give you this formula on the exam. So that right there is 9. Okay, so its effective nuclear charge, these electrons now feel a really strong charge. 9. Okay? Okay. Alright, so that's the effective nuclear charge. And I also ran through the valence electrons with that as well. So these are all the valence electrons for those elements in this group. Now you could just figure out the valence electrons by looking at your diagram. I'll give you 3 different copies of that diagram for the test.
Wait, which diagram?
A diagram that looks like this.
Oh, those.
So
Okay.
then
Yeah.
the
Except
valence,
I redid it. I revised it, and I also put numbers down below so you can count a little bit easier. Double check a little bit easier. In fact, I can give you guys the. Yeah, I'll do that.
Review session goodie bag? Review session party favor.
Yeah, I usually give these out. But you guys can keep these.
Mr. Stan, I have a question.
Yeah.
thanks, man.
So it's NA plus 1. It's plus 1 because it's in the first group? Or that has nothing to do with it?
Actually, that does have something to do with it, but for our purposes right now, the first one I just picked that.
Oh, okay.
For all you know, I could have picked plus 3. Okay? It just so happens that normally is what happens.
And the valence would be the last dot.
The valence
the
is
whole
the
shell.
yeah, this whole shell. So this whole shell right here is the valence shell. All of these dots right there represent all the electrons in the valence shell. So those are called valence electrons.
Good.
Okay. Okay. Got it? Kind of.
Yep.
Better, yeah.
Okay.
Wait, would it ever? These are all like positively charged right now, correct?
This is positively charged. This atom is positively charged. Yes.
No. So wait, would you ever one that's negatively charged or no?
Yeah, we could do that. We could do a negatively charged one. Let's do a difficult one that's negatively charged. Okay, how about that? Let's do. And this one's not that difficult. Let's let's do, I don't know, oxygen. Let's do a negatively 2 charged oxygen atom. Okay, let's try to find the effective nuclear charge of the valence electrons of oxygen if it's -2. Actually, let's do -3. This never happens, but it's just an example. It's difficult. This never happens in nature, but we'll just do one that's difficult, okay? Alright, so the formula again is the number of protons minus the core electrons. So for oxygen, how many protons do you have for oxygen?
You'd have 8.
You've got 8 protons. Okay?
So would you have 11 electrons?
So normally you would have 8 electrons, but now we've got 11 total electrons.
Yes.
Right? So what does that look like for our valence electrons though? So what's the, if we want to write this out, it's going to be 2-8-1, right?
Yeah.
So now we have 10 core electrons, right? And we've got 1 valence electron. So it's going to be 8 minus 10, which will give us a -2 charge,
Okay.
which doesn't make a whole bunch of sense. But that's how you'd figure this out. I'll do this really quickly, and I'll just erase this and do -2. Let's do a different example. It's a little bit more common sense. -2, okay? So here, there's 8 protons minus the number of core electrons. But if you write out its electron configuration here,
I don't know why you
Oops.
did 8-10 before.
that would be
You
Right
did
here.
2.
this is its electron configuration, sorry. It looks like 2 minus 8. This is the electron configuration now, oxygen. Because it's got this -2 charge, that means we've got 2 extra electrons. Normally, this would be 2-6. And you can put that into your chart right here. If you put in 8 electrons, it's going to give you 2-6 as your electron configuration, right? So you'll have 2 core electrons, and you'll have 6 valence electrons. But now, we've added an extra 2 electrons. So this electron configuration now is going to be 2-8. But the formula says protons minus core electrons. So our protons, 8, and our core electrons are 2. So this is the ZF. 8 minus 2, which is
6.
6.
Okay.
So those are some Z-effective problems. Those are just the kinds of problems I'd give you on the test. And that one right there for magnesium, the one that was positively charged, I'm sorry, sodium that was positively charged,
Yeah.
that's a kind of a tricky problem. It's the hardest kind of Z-effective problem I can give you. So if that makes sense to you, or if you think it makes enough sense that you can go home and watch this again and again, and then it'll make sense to you, and you can come back on Monday and ask another question about it, and you think it'll make sense to you, then you're on the right track.
Okay.
Okay? Alright, so that's Z-effective and, and valence electrons, so we can kind of erase those. So now we just got to talk about trends. And this is the part that gets really confusing really quickly.
Fine.
Well, that's so fast.
So let's go really fast. Alright, Ben?
Yeah.
Oh, yeah.
What is this cutting off? 14 minutes?
Yeah. Let's see.
Wait, I've got it here.
3, 2.